Good evening, my YouTube viewers. Crystal here. What I wanted to do tonight was I wanted to follow on from the video that I made yesterday about imbalanced data sets. And I started out using the data set about agriculture, but it had the effect of crashing my system because my computer is not very powerful. So I went on to Jason Brownlee's site and I got a data set on E. coli, and I decided that I would use that to determine which models are best for imbalanced systems. And so what I did was I took a series of models and I put them and I used them with this E. coli data set to actually determine which model is best. And we're going to talk about that as I go over the program. So the first thing I did was I loaded the libraries. You can see the libraries right here. And then I loaded the data sets, and I got this data set off of Jason Brownlee's GitHub account. But the data set did not have any column headers, so I had to assign the column headers. And so I didn't know what all the tests were for, because what they do is they do a series of tests on a person to see if they have E. coli, and the columns are the tests that they take, but I don't know what the tests that they are, so I just wrote reading 1 to 7 and then the result. So reading 1 to 7 are your independent variables, and your result is your dependent variable, which is your Y variable. And so that's what I did. So I checked for any null values. On this particular data set, there were not any null values. The data was complete. Then what we did a graphical representation of the E. coli data set, and so you can see how the result affects all of the other readings. And then what we wanted to do is I wanted to compare the result to the independent variables. So we did a group by a result, and then we did a sum. So you can see there were 8 different variables. It says right here there were 8 different outcomes. We had 7 rows. We had seven rows of data, but we had 8 different outcomes. So what we had to do was we had to label and code the result, because the computer wants to see numbers. So what we did was we label and coded the result. And then what we wanted to do is we wanted to count each class, because we had a class imbalance. And so you can see class number 2, you only had 2 of those classes in there. And class number 3, you only had 2 of those classes in there as well. And class number 6, you only had 5 of those classes. So we had a definite class imbalance on this E. coli data set. Then what we wanted to do, I just wanted to check the percentage to see the percentage of every class. So we had 42.39% class 0, 22.99% class 1, less than 1% class 2, less than 1% class 3, 10.45% class 4, 5.97% class 5, 1.49% class 6, and 15.52% class 7. So what we did was we broke down the occurrence of each class, and I multiplied it by 100. I divided it by the length and multiplied it by 100 to get a percentage. And now what we've done is we have a graphical representation, and the graphical representation shows you the class imbalance very clearly here. So now what we've done is we've assigned our X and Y variables. So your Y variable is your dependent variable, and that's train.result. And your X variable is your independent variable, and it's train.result axis equals 1. So you can see your Y variable, which is just an array of numbers from 0 to 7, and then you can see your X variable, which is a data frame, which now does not include the result. So now what we've done is we've set up our training set into train test split. So X train X val, Y train Y val equals train X split. XY random state equals 27. In this instance, I set a test size of 50%, and stratify equals yes because you have a class imbalance, and stratify has to do with cross-validation, and it does like a stratified fold cross-validation, and that's what it means when you put stratified to yes. We checked our shape, so X train is 167.7 and X shape is 168.7. Y train is 167 and Y shape is 168. So now what we've done is we've checked the count values for Y val, because that's what we want to see. We want to see how many we have of each class in your Y val column. And here you can see we have a data frame, we have a visual representation of Y val in addition to the counter. Because the counter is going to come in handy, I used a sheet of pencil and paper or pen and paper to write all the variables down, all the values down. So now what we do is we define our model. And when we define our model, I used several models to see which model was the best. So we checked logistic regression. I know it says logistic regression CV here, but it's not true. So we use logistic regression, and we have to set it up for a multinomial for the multi-class, and then we have to set up class weight is balanced. And I set it up for a max iteration of 2,000, but I still got a warning about the max iterations anyway. And then we have to fit our X train and Y train into the model, and we get an 88.62% accuracy when we use logistic regression. So now what we do is we predict on our validation set, and we have an 88.55% accuracy when we predict on our model. And then what we do is we create a matrix, and it's important that you create a matrix on any time that you are dealing with classes, so you can see how many values of each class that you have. And that's important to do because you can see over here 0, 1, 2. Number 2, we don't have anything, and number 3, we don't have anything. So logistic regression did not pick up the class imbalance, even though we set it up the stratify equals yes, and the class weight equals balance. So now what we did was we checked our random forest classifier, and we set our class weight up to balance. N estimators equals 50, and random state equals 0. I suppose if I wanted to, I could have fine-tuned it more, but even with the hyperparameter tuning that we used, we still got 100% accuracy on this data set when we fitted it with X train, Y train. And what we do is we predict on our validation set, and we had an 84.52% accuracy when we predicted on our validation set, which is about close to 3 or 4 degrees higher than logistic regression. But when you look at your confusion matrix that was completed on it, you still 0, 1, 2. On column 2, you don't have anything, and then column 3, you don't have anything. So this model did not pick up on the class imbalance, even though we had set it up for balancing. The next thing we tested on was the decision tree classifier, and we set the class weight up to balance as well. And when we fitted it to X train, Y train, we've got 100% accuracy. But when we made a prediction on the validation set, we only had 76.79% accuracy. And we created our confusion matrix. And you can see here on column number 2, there are not any values. So again, this decision tree did not pick up the class imbalance. Now what I decided to do was to use the extra trees algorithm. And the extra trees algorithm, I set it up as a class weight of balance, and I fitted it to X train, Y train. It had 100% accuracy, but when we predicted on it with the validation set, we had an 85.12% accuracy. But if you look over here at the confusion matrix on 0, 1, 2, column 2 and 3, it did not pick up any of the values. So the next thing we tested was our gradient boost classifier. And again, the only thing we had was a random state. So we set a random state up to 0, but we fit it with our X train, Y train, and we got 100% accuracy. But when we predicted on the validation set with it, we only got a 79.17% accuracy. And when we had our confusion matrix, you see over here on column 2 that it didn't pick anything up on the confusion matrix. So now what we tested was our ADA Boost Classifier to see if the ADA Boost Classifier would pick up anything. When we had lots of parameters because we used it with random forest classifiers being the base estimator, so we had a class weight as balanced, and it had 100% accuracy when we fitted it with X train, Y train, and when we predicted on the validation set, it only had an 85.71% accuracy. And when we programmed in our confusion matrix, you can see on column 2 and 3, it still didn't pick up any of the imbalance classes. So now we check Mlp Classifier, which is like a deep learning, which is deep learning. We set it up for max iterations. And when we fit it with the X train, Y train, we got an accuracy of 91.62%. When we predicted on our validation set, we had an 85.12%. But when we created our confusion matrix on number 2 and number 3, it still did not pick up on any of the imbalance classes. Now what we did was we used a bagging classifier, because what I did was I went through sklearn and I was trying to find out were there any models in sklearn that I can use that I don't normally use. And I found something called a bagging classifier, and you can find that in the sklearn website. And we used SVC along with the base estimator for the bagging classifier, and we had a class weight of balanced. But that still isn't right. That's not right. So this is a really short program, so hopefully it'll run very quickly. So that means I'm going to have to rewrite all of this stuff that I had previously written up, because I had written it up on a sheet of paper, and I wrote it up on a sheet of paper, and I noticed all the values were the same, and I thought, well, there's something wrong with that. And so I found out what was wrong with it, because I fitted on X and Y instead of X train, Y train. So we had 84.43% when I set it up on X train, Y train, and when we predicted on the validation set, we had 81.55%. And you can see here on the bagging classifier, you can see on number 2 and number 3, it picked something up. So that was a good model to use, is the bagging classifier, because it actually picks something up. And what I'll have to do is I'll have to write this down. So it's a good thing that I actually make these videos and go over the text with you on the videos, because I can pick up mistakes. So the next thing that we checked on was something called Gaussian NP, and that was something where I went into the sklearn website to see if there were any models that they have that I don't normally use when I'm making my predictions. And Gaussian NB was a model that I don't normally use. And that's the good thing about looking on the sklearn website, because if you look on that website, you can find all different kinds of models and things that you can try out, and that's what you're supposed to do. That's what being a data scientist is all about, is trial and error. So that's what this video is about, trial and error. So on the Gaussian NP, we had 86.83% when we fitted it on the X train, Y train. And when we predicted on our validation set, we had 80.95%, and we created our confusion matrix. And you can see here that when we created our confusion matrix, it did actually pick up on columns 2 and 3. So what I wanted to do was, with this Gaussian NB, to have something called a partial fit. And I decided that I would set it up for a partial fit to see what would happen if I set it up for a partial fit. And I had 86.83% on the X train, Y train. Let's compare that to, it's the same. It was the same. And then we had 80.95% when I predicted on the validation set. And that was the same, because I just wanted to see if the values for a partial fit would be any different from the values for fit, because this particular model allows you to have a partial fit. And I wanted to try that out. And so we looked at our confusion matrix, and you can see the confusion matrix that you have something on column 2 and 3. So that was a good model to use. The next thing I used was the Xgb Classifier. And I had originally only wanted to use functions from the sklearn library, but I decided that since Xgb is such a popular model to use, I decided to go ahead and use it anyway. So we fit our X train, Y train to the Xgb, and we got 100% accuracy on that. And when we predicted on the validation set, we got 82.15% accuracy. And we checked our confusion matrix, and we had it picked up values on column 2 and column 3, which means it's a good set. So basically, what has happened is on the bagging classifier, the Gaussian MB, and the Xgb, it picked up values on the class 2 and class 3, but the other models that we used, it didn't pick up any values. So what that just says is that logistic regression, CV, random forest, decision trees, extra trees. You had something called a GB, that's gradient boosting ADA, and you have something called MLP, which was a deep learning. Those were not able to pick up the imbalanced classes. So they weren't good to use. You may have had a high accuracy, but it didn't pick up the imbalanced classes. The only models that you were able to pick up the imbalanced classes were bagging classifier, Gaussian NB, and Xgb. And I'm sure I could have checked other models, but I just decided to stop at Xgb because I was a little bit tired from doing all this studying, and I wanted to make a video to show you my results, and I'm going to be making a blog post on this as well. So if you like my video, please like, subscribe, and share, because this gives you the results of the experiments that I was conducting on the E. coli dataset that I got from Jason Brownlee's GitHub account. And if you like the work I do, if you want to leave a donation, I have my email address to the PayPal account down below. I don't have enough subscribers to monetize, so the only way I can make any money on this channel is to ask for donations. And thank you so much for watching this video. I'm also going to be making a blog post on the results of this, so you can look out for that. And I look forward to making other videos for you as well.